Welcome students, welcome to today's session of All4 e-learning program. In the last class, we have studied about different results of applications or results of the thermal expansions of solids. Results of some practical results of the thermal expansions of the solids. We have mentioned about a platinum wire to be fused in glass. Whenever we have to fuse in glass, we are using platinum wire because alpha is the same. Similarly, we have given a practical result that when we are laying cement roads, we are keeping a small gap, and whenever there are railway track constructed, we are leaving a small gap. So like this, we have some results given in the last class. And now in the last class itself, we have discussed about isotropic and anisotropic solids, and how the values of alpha will be different in different directions, that we have discussed. Now in the present class, let us move into the further details about isotropic solids and anisotropic solids, the values of alpha. As we have studied in the previous class, isotropic solids are those solids which expand equally in all directions. That means if you take a cubic body, if you take a three-dimensional body like a cube, the length and breadth, height, everything will be expanding uniformly, so that coefficient of expansion along the x-axis, coefficient of expansion along the y-axis, coefficient of expansion along z-axis, all of them are equal. That is the property of an isotropic solid. Now for an isotropic solid, we can have a relation between the coefficients of expansion alpha, beta, gamma. Alpha, beta and gamma. How to establish this relation? Now let us go for this derivation. Let us consider a cube. Let us consider a cube of dimension 1 meter. That means it has 1 meter length, 1 meter breadth and 1 meter height. So it is a cube of 1 meter. That means length of the cube in any direction is 1 meter. And if you consider area, let us say initial area, you take any face, because it is a cube, each face is a square. Each face is a square. So area is, for any face you consider, the area is 1 into 1. So it is 1 meter square. And similarly, if you consider the volume, the initial volume, because it is length, breadth, height, each equal to 1 meter, so it is 1 into 1 into 1 or 1 meter cube. So these are the initial values of length and area of volume. Length you can take in any direction, and for any face you can take the area, and the total volume is 1 meter cube. Suppose it is made up of a material whose coefficient of linear expansion is alpha. It is made up of a material whose coefficient of linear expansion is alpha. Now I am increasing the temperature of this body by a change of temperature equal to 1 degree centigrade. Just the temperature of the body is increased by 1 degree centigrade. Then as per the equation, final length in any direction, if you observe, L2 equal to L1 of 1 plus alpha delta T, that equal to initial length in any direction is L. We say it is initial length in any direction, we said it is 1 meter. So 1 into 1 plus alpha delta T, the change in temperature was only 1 degree centigrade. So it is again 1. So finally this will become equal to 1 plus alpha. That means initially it is a cube of dimension 1 meter. But now because of increase of temperature by 1 degree centigrade, it is becoming a cube of dimension 1 plus alpha. That means length becomes 1 plus alpha. If you take the breadth also, it is 1 plus alpha. Height also 1 plus alpha. So the unit cube initially having a dimension of 1 meter, now it is having a cube of 1 plus alpha. So length, breadth, height each equal to 1 plus alpha. Now as the length in any direction is 1 plus alpha, let us calculate area. Area of any face you consider, every face is a square of dimension 1 plus alpha. So area becomes length into breadth, or because it is a square, 1 plus alpha whole square. let us expand. It is 1 plus alpha square plus 2 alpha. 1 plus alpha square plus 2 alpha, that is the final area. And similarly, if you calculate the final volume, it is 1 plus alpha whole cube. 1 plus alpha whole cube. Let us expand. It is like a plus b whole cube. So a cube plus b cube plus 3a square b, 3 into alpha, plus 3a b square, it is 3 alpha square. These are the area, final area of each face and final volume of the total cube. And final length is 1 plus alpha. So we have the initial values, length is 1 meter, the final length is 1 plus alpha after increasing the temperature by 1 degree centigrade. And similarly, if initial area is 1 meter square, the final area is 1 plus alpha whole square or 1 plus alpha square plus 2 alpha. And final volume, initial volume is 1 meter cube and final volume is 1 plus alpha whole cube. It is 1 plus alpha cube plus 3 alpha square. You are getting the value like this. Now let us find out the values of beta and gamma for this body. To get the values of beta, what is the value of beta? Beta equal to change in area divided by initial area into change in temperature. We can use this equation to calculate the value of beta. So let us calculate the value of beta. What is change in area? Final area is 1 plus alpha square plus 2 alpha. So it is 1 plus alpha square 2 alpha and minus initial area is 1. So change in the area becomes alpha square plus 2 alpha divided by initial area is 1 and change in temperature is also 1. But remember, alpha, beta, gamma, we said these are the properties of the material. Properties of the material, that is properties of material of the cube. And in general, they will be having values of the order of 10 power minus 6 per degree centigrade. So because of this very small value, 10 power minus 6, when it is square, when you take alpha square, it will be of the order of 10 power minus 6 whole square, 10 power minus 12. Which is numerically negligible. So we need not consider the value of alpha square. So when you neglect the value of alpha square, because it is negligibly small numerically, we can write beta equal to 2 alpha. Beta equal to 2 alpha. This is only 1. So we get a result beta equal to 2 alpha for a solid like this. And similarly, let us calculate the value of gamma. Gamma is change in volume divided by initial volume and change in temperature. So delta V by V of delta T, that is the value of gamma, where delta V is the change in the volume and V is the initial volume, delta T is change in temperature. Let us apply the values. What is final volume here? 1 plus alpha cube plus 3 alpha plus 3 alpha square minus initial volume is 1. So when this 1 is cancelled, you are left with alpha cube plus 3 alpha square. So delta V is alpha cube plus 3 alpha square plus 3 alpha by volume. Initial volume is 1. Change in temperature is also 1. Now once again, let us consider the same argument, because alpha is of the order of 10 power minus 6. Alpha square term, that is of the order of 10 power minus 12. Alpha cube term, that is of the order of 10 power minus 18. All these are negligible terms. Numerically, they don't have any value. So when alpha square and alpha cube terms are neglected here, what you get finally is 3 alpha. So you are getting gamma equal to 3 alpha. So we got beta equal to 2 alpha and gamma equal to 3 alpha. This is the case of an isotropic solid. So for an isotropic solid, if you take the ratio of alpha is to beta is to gamma, that will be equal to alpha is to beta is 2 alpha and gamma is 3 alpha, so that the ratio becomes 1 is to 2 is to 3. So this is an important point we have to remember. Alpha, beta, gamma for an isotropic solid are in the ratio 1 is to 2 is to 3. So that when you consider these values, we can write like this. We can write that from that equation beta is 2 alpha and gamma is 3 alpha. Suppose I want to express the value of gamma in terms of beta. Let us consider gamma equal to 3 of. I want gamma in terms of beta, but you know beta equal to 2 alpha, where you can write alpha as beta by 2. So this becomes 3 beta by 2. So gamma is 3 beta by 2. Or if you want beta in terms of gamma, it is 2 gamma by 3. Like this, we can give the ratio between them. But very important thing we have to remember is alpha is to beta is to gamma is 1 is to 2 is to 3. This is the important relation we have to find out. What is the importance of this relation? Now, previously when we are discussing about relative changes and percentage changes for an isotropic solid, let us suppose we are calculating. If you consider relative change delta L by L, that is alpha delta T, and percentage change if you consider, multiply with 100, alpha delta T into 100. Now let us consider percentage change in area. So delta A by A, this is the relative change. Let us multiply with 100. You are getting the percentage change. But practically we have shown that it is beta delta T into 100. But now we have shown that beta is equal to 2 alpha. Beta equal to 2 alpha. Therefore, let us use that value. It is 2 alpha delta T into 100. That is nothing but 2 of, what is alpha delta T into 100? It is the percentage change in the length. So, delta L by L into 100. That means percentage change in area is simply double the percentage change in the length. Double the percentage change in the length. Directly you can write. If the percentage change in the length is 5%, percentage change in the area, directly you can multiply 2 into 5, 10%. That is possible only because alpha, beta, gamma are in the ratio 1 is to 3, 1 is to 2 is to 3. And now if similarly if you calculate percentage change in volume, percentage change in volume is delta V by V multiplied by 100. Let us consider percentage change in volume, delta V by V into 100. Delta V by V into 100, we have shown that it is gamma delta T multiplied by 100. But now we know gamma is 3 alpha. So 3 alpha delta T into 100. So it is 3 times percentage change in the linear expansion or length of the body. So by knowing the percentage change in length, double the value of, when you multiply with 2, you will get percentage change in area, and by multiplying with 3, you will get the percentage change in volume. So that the percentage changes will also be in the ratio 1 is to 2 is to 3. So this is the importance of this relation. So we have to remember this is the relation applicable for isotropic solids. What about anisotropic solids? For anisotropic solids, we have given that coefficient of linear expansion, it will be different in different directions. Then in such a case, if alpha x and alpha y and alpha z are the coefficients of linear expansion along the x-axis and y-axis and z-axis, we will get the average value of alpha by the equation alpha equal to alpha x plus alpha y plus alpha z by 3. You are getting the average value of alpha, because when it is an anisotropic solid, it expands by different amounts in different direction. So when you are specifying the value of alpha, you have to give the direction. But we are taking the average value of alpha. Then how to get the average value of alpha? You will get the average value. And similarly, by cross multiplication, we can take 3 multiplied by average value of alpha. That is nothing but gamma. So that gamma will be equal to alpha x plus alpha y plus alpha z. We can use this relation also in case of anisotropic solids. Remember the ratio alpha, beta, gamma in the ratio 1 is to 2 is to 3. This is not applicable for anisotropic solids. It is applicable only for isotropic solids. So this is about the relations between alpha, beta, gamma as far as isotropic solids are concerned. Now let us move on to the applications. Applications of thermal expansions. What we have discussed in the last class, it is results of the thermal expansions. Now let us go to practical applications. what are the practical applications of the thermal expansions of solids? Let us go by one. First, let us take the expansion of rails, that is a railway track. When we are explaining about this application, we said that whenever a railway track is constructed, there will always be a gap is left between the rails. Gap is left between the rails, and this gap is to allow the expansion of the rails, because it is exposed to the atmospheric conditions. Depending upon the change of temperature, that will be expanding. To allow the expansion, we are leaving the gap. Now let us suppose what will be the value of the gap to be left. When we discuss here about the gap to be left, we should remember one important thing. Suppose there is a rod. When the rod is heated, we said it expands. But how it expands? Expansion will be taking place in the direction where it is free. For example, a rod is taken like this. It is suspended from a fixed point or fixed between the midpoint, and it is heated. Both the ends are free. So expansion will be taking place this direction and here also. So if it is initial length is L and change in the length is delta L, you can see a change in the length delta L by 2 in this direction and delta L by 2 in the opposite direction, because both ends are free. Suppose the same rod it is placed on a horizontal surface standing vertically. Suppose it is fixed to a stand. It is fixed to a stand and we are heating it. Now the end here is not free. It is fixed here. It cannot go down. As a result, the total expansion will be in the upward direction, and this is the length of the body. So expansion will be in the direction where the body is free to expand. So here in the case it is rod, the rod is free to expand both the directions. So expansion is equally distributed. But here the rod is fixed here. It cannot expand in the downward direction. So entire expansion will be upwards. In any case, change in the length is delta L. It will be the same. But expansions, if you observe, because both ends are free here, it will be expanding on both the sides. But here expansion will be in only one direction. Now, considering this idea, when you are taking the railway track like this, this rail will expand and this rail will also expand. Both of them will expand. But because both are free at the other end, because there will also be a gap for this rail, and here also for the other rail also there will be a gap. So this is free to expand on both directions. Similarly, this is also free to expand on both directions. Let us say delta L1 is the expansion of this rod, and suppose L1 is the length of this rail and L2 is the length of the other rail which are meeting here. And let us say delta L2 is the expansion in the second rail, but now they are meeting here. So as per the discussion, because it is free, the expansion of this rod in this direction is delta L1 by 2, and expansion of this rail in this towards left, it is delta L2 by 2. Therefore, to allow the expansion of this rail of length L1, there must be a gap of delta L1 by 2. To allow the expansion of this second rail, it is the gap required here is delta L2 by 2. So the total gap required, let us say it is delta L equal to delta L1 by 2 plus delta L2 by 2. That means it is the average expansion of the two rails which are meeting at that point. Simply we can say this is equal to delta L1 plus delta L2 by 2. Delta L1 plus delta L2 by 2. Because sometimes the rails may not have same length. When the length is different, they will be expanding in a different way. So what is the total gap is average expansion of the rod, of the rails, of both the rails you can place here. Suppose all the rails are having same length. When all the rails are having same length, L1 and L2 are equal. L1, L2 are equal. So delta L1, delta L2 are also equal. Then you will have delta L1 plus delta L2 by 2. It is simply equal to delta L. So the gap to be left let us say this is gap now. So the gap to be left between the rails, that is equal to average expansion when the lengths are not equal, and if the lengths are equal, simply you can say the expansion of each rail, what is actually present there, that much of gap is to be left. So consider these two cases as both are important. Generally the railway track, when you are constructing, all the rails will have the same length. Then directly you can say delta L, which is nothing but L alpha delta T, where L is the length of each rail and alpha coefficient of linear expansion, delta T corresponding change in temperature. Directly you can measure. But in a special case, if the lengths of the two rails are not equal, which are meeting at a point, then use this relation, the gap to be left equal to average expansion of the two rails meeting at that point. So this is one calculation regarding the gap to be left between the rails. Now let us move on to another application related to the same condition. Sometimes when we are solving with the problems, we will have a question that the distance between two successive stations, suppose there is a railway station A here and there is a railway station B here. Let the distance between them, let us say it is x. Suppose it is a 30 kilometer or 40 kilometer. So there are two stations separated by a distance, let us say x. Now between the two stations there will be a number of rails, they will be joined. Between every two rails present there is a gap. Then we are asked to calculate the total gap, sum of the gaps. Then we don't know what is actually each rail is, length of each rail, how many gaps are there, we don't know the number of gaps, but we want the total value of the gap to be left between all the rails present between the two stations. Then what we have to do? Use this equation, take the total length of a single rail whose length is equal to distance between the two stations. So if x is the distance between two stations, you consider that there is a single rail whose length is x, and consider the expansion of that particular length, you will get the total gap. So the total gap to be left equal to the distance between the two stations, that is x into alpha into delta T, where delta T is the change in temperature. So total gap to be left equal to distance between the two stations, alpha coefficient of linear expansion into delta T. Directly you can calculate this distance, the total gap present between the two stations. That means even though we are not knowing the length of each rail and how many gaps are there, all these things are not known, but sum of the total gaps we can find out from this relation, that is total gap to be left equal to total distance between the two stations multiplied by alpha coefficient of linear expansion into delta T. So as far as applications of rails are concerned, we can use these two conditions. Now let us move on to another application. Second important application, that is due to metal scales. This is an important application. Generally we use the scales made up of glass or plastic, but sometimes we use metal scales also, so that every time it will not break. But when you are using metal scales, we must take care about one condition, because on a scale we will be having the markings or graduations. Suppose we have taken a meter scale. On one end you will have 0 centimeter, at the other end you will have 100 centimeter, so that the total length of this scale that will be divided into parts like this. If there are, you can say, if you assume that there are 100 parts, each part corresponds to 1 centimeter. If there are 100 lines like this, you can say that each one is 1 centimeter and total length is 100 centimeter. It is a meter scale. But when the graduations are made on this scale, they are marked on the scale, that is taken place at a particular temperature. Suppose at 20 degrees centigrade this scale is prepared. The scale is prepared at 20 degrees centigrade. That means the gradations are developed or marked on the scale at the temperature. Now suppose you are using the scale at a very high temperature around 80 degrees centigrade. Then what happens? Corresponding to it is perfectly prepared to measure at 20 degrees centigrade. But we are using at a very high temperature. So corresponding to this change in temperature, it will be expanding. When the length expands, the length of the scale will not be equal to 1 meter. Because it is expanding, initial length is 1 meter. But because of expansion, the total length will be something more than 1 meter. Something more than 1 meter. But practically if you observe, this end will always be 0. This end, even though it expands, all the distance between every two lines will expand. The two lines present here, let us say they are present at this much of distance. This is 1 centimeter. But now the distance between them is slightly increased. As a result, all the lines are moving away. But one end will always be 0. Second end will always be at 100. So it appears to be a meter scale at all temperatures. But it is not correct. Why it is not correct? At higher temperature, because it is expanding, the length is increasing. So the true length, actual length, it is more than 1 meter. Suppose it expands by 1 centimeter, its total length is 101. But even then, the scale represents 0 at this end and 100 at this end, so that it appears to be a meter scale. And suppose in other case, we are using this scale prepared at 20 degrees centigrade at a temperature minus 40 degrees centigrade. Then what happens? Because of decrease of temperature, it will be contracting. A substance which expands very high, that also contracts very high. That means large value of alpha not only gives that the expansion is more, but it also indicates that contraction is also more. That means alpha represents the change in the length, whether it is expansion or contraction. So when alpha is more, contraction is more, or expansion is also more. So corresponding to same change of temperature, that is 60 degrees centigrade, suppose it contracts by 1 centimeter. When it contracts by 1 centimeter, the final length, that means the lines are coming close. Now they are not this much distance. The distance has come down. It is so small that we cannot identify. It is so small. The contraction or expansion between two successive lines, it is so small that we cannot determine. But practically, definitely, there is expansion. Therefore, as a result of contraction, when it is contracting as a whole by 1 centimeter, the total length now, it is only 99 centimeter. But as the lines are coming down, this end always reads 0, this end always reads 100. But practically we know its length is only 99 centimeter. So when you are using a scale at a temperature other than the temperature at which it is graduated or markings are made, it is prepared to measure the correct reading at 20 degrees centigrade. But now you are using at higher temperature. Definitely in such a case we need some correction. The practically measured value and the true value, they are quite different. Then how to measure the true value under the two conditions? Now to understand clearly, let us consider how it is expanding and contracting. When you are using the scale at a higher temperature, we said its length is not 100 but the length is 101. That means true length is more than the practically measured length. The practically measured length as suggested by the scale is only 100. But we know its true value is 101 centimeter. So the correction we have to add. What is that correction? Correction is nothing but expansion of the scale. The expansion of the scale is the correction. So we have to add. Therefore, in such cases, that is when you are using the scale at a higher temperature, higher in the sense more than the temperature at which it gives the correct reading. All metal scales will give correct reading only at a particular temperature. At all other temperatures, definitely it needs some correction. Then how to go for the correction? Now, in the case suppose you are measuring at high temperature. At higher temperature, the true value is nothing but the measured value plus expansion. So measured value of 1 plus alpha delta t. 1 plus alpha delta t. Because it is initially 1 meter, 1 into alpha into delta t. That is the expansion. So measured value is 1 meter and additional value is 1 meter into alpha into delta t, which represents the expansion. Therefore, the true value at higher temperature, at higher temperatures, the true value is given by measured value of 1 plus alpha delta t. That we have to explain. Now, suppose you are using at a lower temperature, much lower temperature than the temperature at which it gives the correct reading, then we have to subtract. Take that example. At lower temperature, we have taken a meter scale. It is its length is exactly 100 centimeter at 20 degrees centigrade. But when you are using at minus 40, we explained now, it contracts by 1 centimeter, but final length is only 99 centimeter. But the scale represents only 100 centimeter. The true value is different. Then why it is getting wrong value? To make the correction, because of contraction it is giving the wrong value. But to make the correction, now we have to subtract the contraction. Practically it always shows 100 only. This end will always be 0. This end will always be 100. So it always gives the same reading, 100 centimeter. But practically we know it is contracted by 1 centimeter. Its original length is only 99. So from the reading what you are getting as a measured value, subtract the expansion. Then the true value corresponding to a low temperature, it is nothing but measured value of 1 minus alpha delta t. So here measured value multiplied by alpha delta t, that represents the contraction, and here that represents the expansion. So use these two conditions to find out the true value. To find out the true value, we can use both these equations. Now with this application, let us close today's class, and in the next class we will discuss about all other applications of thermal expansions of solids. Right? Thank you.